Let's talk for a moment about chemical compounds. Chemical compounds are made by sticking atoms together. The periodic table of the elements represents all of the atoms, types of atoms, that are known to chemists. In some sense, it's an alphabet for making materials. Each of the atoms themselves have their own set of specific properties. When combined, the resulting mixture has different properties. And so in some sense, I can look at the periodic table as being kind of an alphabet for writing words. And so carbon, atomic symbol C, carbon can be arranged multiple ways with really pretty much any of the elements in the periodic table in some way, shape, or form to create millions and millions of different compounds. I essentially have an alphabet that has 100 letters in it. And so you can imagine the variety of words I could write. That would be a very complicated language. I mean, English only has 26 letters in it, and there are tens of thousands of relatively common words. And any one of those words is useless to you if you don't know what it means. Chemical nomenclature actually simplifies the process, where the words that I write are not standalone with meanings that I need to memorize. The words will tell me the composition. At its essence, chemistry is about doing reactions. We talk a lot about physical properties and material properties, which are sort of independent of a chemical reaction, but that's as much physics or engineering as it is chemistry. If you really wanted to scope out chemistry as a field, chemistry is about doing chemical reactions. And chemical reactions are simply rearranging my letters, my atoms, to make new materials. The symbols in the periodic table give me a shorthand for representing each of the different types of atoms that go into making up a molecule. It is simply easier to write C for carbon than to write out carbon. And so water, as you may know, is made up of two hydrogen atoms stuck to one oxygen atom. So the molecular symbol for water is H subscript 2O. The subscript indicates that there's two of the preceding atomic symbols. And so this molecular symbol actually tells me the composition. It doesn't tell me exactly how they're hooked up, and I don't need to care. What it does tell me is that water has two hydrogen atoms and an oxygen atom that are somehow stuck together. Now, water is a common name. In order to know that water is made up of two hydrogens and an oxygen, you'd have to have memorized the molecular formula, H2O, that corresponds to water. That would make for a whole lot of memorization. There are more than 10 million compounds that have been identified and cataloged, and to memorize that, Freddie J is C2H3O2N2O is a whole lot of memorization. So rather than give every molecule a common name like water, chemical nomenclature gives a systematic name to each of the molecules that tells me specifically what the chemical composition is. Ultimately, this gives me an efficient way to write chemical reactions so that anyone who sort of speaks the language of chemistry can understand my point. Now, for example, this is one of my favorite reactions for reasons we don't need to get into here. Right? Hydrogen and oxygen can react to form water. That is a verbal statement of a chemical reaction. Even more specifically, since hydrogen and oxygen are diatomic elements, what I'm really saying is that two diatomic hydrogen molecules and one diatomic oxygen molecule will react under a certain set of conditions to form two molecules of water. the ones and twos that I've mentioned in my description are necessary to balance the total number of atoms in the equation. But of course, even that simple reaction becomes a mouthful. I've got a whole sentence there. It's much easier if I can write it in a chemical shorthand. And the chemical equation is that chemical shorthand. Here's my atomic hydrogen. Again, it's a diatomic element, so there's 2 hydrogen atoms in it. Here's my oxygen element. Again, it's diatomic, so there's 2 oxygen atoms in it. And essentially what I've got is 4 H's and 2 O's that get turned into 4 H's and 2 O's. They are just hooked up differently. And we'll talk later about balancing chemical reactions, but fundamentally, that's what I'm doing. I start with hydrogens that are bonded to other hydrogens, 2 of them, and an oxygen that's somehow bonded to another oxygen, and I separate them from each other and hook them up into water molecules. Right? Notice that's the reason for my 2's. In order for this reaction to balance properly, I have to be keeping track of all the atoms. Right? There have to be the exact same number of atoms on the left-hand side of my arrow as there are on the right-hand side, so that I know where all the atoms went. So I've got 1, 2, 3, 4 hydrogens here. I've got 1, 2, 3, 4 hydrogens on the right. I've got 1, 2 oxygens. I've got 1, 2 oxygens. That's a balanced chemical reaction, which is really just identifying where the atoms come from. Right? What's my source of atoms when I start the reaction, and where they ended up in my products. And of course, this is much simpler to write than the sentence that describes what happens. 2 diatomic hydrogen molecules and 1 diatomic oxygen molecule react to form 2, well, water molecules each containing 2 hydrogens and 1 oxygen. That's a whole lot of verbiage. Right? This is very neat symbolically. But if I wanted to express it verbally to someone, I need to be able to translate my symbols into words, and if I want to write it symbolically, I need to be able to translate my words into symbols. And that's what nomenclature does for me. It creates a language for naming chemical compounds, and because the chemical composition is so important, I need to know the number of each atom. The language I've adopted tells me what the molecular composition is. And there's essentially 2 different systems that we'll talk about. There's actually a third system, organic compounds, but that's sort of a separate topic that we'll talk about later. Here we're talking about inorganic compounds, and they really come in 2 types. And identifying the types, it's really helpful to be able to identify metals and nonmetals in the periodic table, because the distinction between the 2 types is a function of which metal or nonmetal is used to make up the compound. Right. So here's my periodic table. Right. The left-hand side in this particular table doesn't actually have a drawn-in step. Right. Everything to the left of my little stair step here is a metal. Hydrogen's a little ambiguous, but it's often grouped as a metal and also included as a nonmetal. In fact, you'll see some periodic tables that put it in both places. Right? Everything to the right-hand side of my little stair step is a nonmetal. And technically, the things along the border are sometimes called semimetals, but it's not an issue for what we're talking about here. Right? This bottom group, the lanthanides and actinides, also count as metals. Okay? And there's essentially 3 ways you could arrange 2 different things. Right? I could take a metal, mix it with a nonmetal. I could take a metal and mix it with a metal, or I could take a nonmetal and mix it with a nonmetal. Right? What I ultimately do in my mixing creates different kinds of compounds that have different properties. And unfortunately, they also are named differently. Okay, metals tend to be electropositive, meaning when they form ions, they tend to be positively charged ions. This is because, and we'll talk about electron configurations later, this is because they tend to be electron poor. Nonmetals, on the other hand, are electron rich. And so when they form ions, they tend to form negative ions. So when you mix metals and nonmetals, if they bond, it's usually because the metal has formed a positive ion and the nonmetal has formed a negative ion. This is called an ionic compound. The metal, which is now a positive ion, and the nonmetal and negative stick together simply because they have opposite charges. Right. A perfect example of such a metal-nonmetal compound is MgO. Magnesium, Mg, is a metal. It's a group 2 metal on the left-hand side of the table. Oxygen is a nonmetal. In this compound, magnesium is actually a 2 plus positively charged ion. Oxygen is actually a 2 minus negatively charged oxygen. Possibly the most important thing in all of chemistry is the fact that opposites attract. And so positively charged ion can't help but be attracted to a negatively charged ion. And so MgO as a compound is formed simply because these two oppositely charged ions are attracted to each other. Right. Because it's a compound formed of ions, it's called an ionic compound. And this is how essentially any metal and any nonmetal form compounds. So as a result, ionic compounds represent an entire class of materials, all formed by a metal and one or more nonmetals, or if you will, an atom from the left-hand side of the table combined with one or more nonmetals from the right-hand side of the periodic tables. As we'll see later, ionic compounds have fairly unique properties, different than other types of compounds, because they really are simply piles of ions. They're not stuck together in the same way that bonded compounds like water are. As a result of all these ions, a couple of the properties that they have is that they tend to conduct electricity very well, and they tend to be soluble in water, at least to a certain degree. And naming ionic compounds is fairly straightforward with one little twist in it. First, the always rules, right? I always name the metal first, and I always name the nonmetal second. The nonmetal has its ending changed to IDE, which represents that it's both an ion and now a compound. Okay, and so for some simple binary compounds, if I take sodium metal and stick it to a fluorine atom, right, where now it's actually a sodium ion stuck to a fluoride ion, I would name this compound sodium metal first, fluorine, the element, gets changed to fluoride, the ion, and so NaF would be named sodium fluoride. Right. NaCl would be named sodium chloride. And Na2O, because now it's Na plus O2 minus, to get the charges to balance, I need two positive charges to balance my two negative charges. And so I need two of the plus 1 ions to balance the minus 2 ion. And so Na2O now would be called sodium oxide. A little trickier because, of course, oxygen, right, had its ending changed to IDE, but it sort of lost a whole lot of its original letters in the process, whereas fluorine and chlorine just had essentially the N changed to a D. Right. So it can be a little tricky, but if it's oxygen, it's always oxide, and once I've done it once, I know it. And life would be just that simple if all compounds were as neat and friendly as sodium and fluorine and chlorine and oxygen. Right? But unlike sodium, which is always a +1 ion when it forms an ion, other metals have different possible charges that they could have when they form ions. And so, for example, if I mix iron and oxygen, I can actually do it two different ways, at least. Right? And the difference is a function of the charges of the ions. Fe2O3 is an iron oxide. FeO is an iron oxide. But they are different compounds made up of different ratios of atoms. And so I can't simply call them both iron oxide. So iron is an example of a metal that can form more than one ion. These charges are sometimes referred to as oxidation states for reasons we can talk about later. But iron can be either a +2 ion or a +3. So in both cases, it's atomically iron, but because it has a different number of electrons, it's +2 in one case and +3 in another. When I'm forming compounds, the compounds are always charge neutral. So of course, mixing an iron 2+ with any negative ion, oxygen, chlorine, fluorine as a negative ion, will take a different ratio to balance than if I take an Fe3+ and I mix it with an oxide or a chloride or a fluoride ion. And so since I've got different ratios, I need to give them different names. And so what I do is actually specify the charge on the metal. This is a little tricky, right, in a couple of ways. One, it's a Roman numeral. If you're not friends with Roman numerals, that can be a little tricky. And second of all, right, it refers to the charge on the ion. That's not so obvious when you first look at the compound. Fe2O3 is actually named iron 3 oxide. But the 3 doesn't refer to anything you see in the molecular formula. Right? The 3 refers to the fact that the iron is a 3+. The iron 2 in iron 2 oxide refers to the fact that the iron is a 2+. But I don't actually see the charge in the molecule. So I actually have to deconstruct my molecule a little bit to see what the charge is. Okay, that can be a little tricky. It's tempting to want to make this 3 into one of the numbers I see, but it's not the number of any particular atom. It's the charge on the metal, only and always. Okay, and so since the iron in Fe2O3 is Fe3+, I call this compound iron 3 oxide. Since the Fe in FeO is a 2+ ion, I call it iron 2 oxide. So the only trick there is recognizing how I know that iron is a 3+. And that's actually easier than it might seem once I show you the trick. Right? But it's important to recognize that number is the charge of the metal always. It's never, never, never referring to the number of any particular atom. Okay? And so I sort of have to amend my naming rules a little bit to include the metals that have multiple oxidation states. I still always name the metal first. Right? I indicate the oxidation state of the metal if there's more than one. For something like sodium that's always a +1, step 2 isn't necessary. Right? So I don't always name the oxidation state of the metal. And then, as before, I name the nonmetal second, and my ending is always IDE. Fortunately, turns out the periodic table is organized in a way that actually makes determining the oxidation states of a lot of the atoms relatively straightforward. Not everything, mind you, but a lot of them. Group 1 is always a +1. Hydrogen actually does have a -1 oxidation state, but that's when it's acting more like a nonmetal than a metal. As a metal, everything in group 1 always a +1. Everything in group 2 always a +2. So for these metals in the first two columns in the periodic table, I never need to name the oxidation state. If it's sodium, I know it's a +1, so I don't need to say it. If it's magnesium, I know it's a +2. I don't need to specify the +2. If I go out to the right-hand side of the periodic table, the noble gases are a little tricky. They don't tend to make a lot of compounds, and when they do, they're sort of bizarre. So I'll ignore those for the moment, right? But group 7, the halogens, are always -1, almost always -1s. The chalcogenides, the oxygen family, are almost always -2s. And so on the left-hand side and the right-hand side of the periodic table, I kind of know the oxidation state, the charge of the ion, just based on what column my atom's in. Where things are a mess are in the middle, in what's known as the transition metals, because all of these essentially have more than one charge that the metal ion could have. And so it's for this group in the middle that I need to use the Roman numerals to specify the charge. Okay. So here's a compound, MnO2. Mn is manganese. O is obviously oxygen. Right. Well, how would I name it? It's clearly a magnesium oxide compound, but because the manganese has more than one oxidation state, I need to specify what the actual charge is on the manganese in this particular compound. There are other manganese-oxygen combinations if manganese had a different charge. And so how do I know what the charge is? Well, in this case, I look at the oxygen, right? Manganese is in the middle, right? It has multiple oxidation states, but oxygen is a chalcogenide, group 6. It's almost always a -2. And so I know what the charge of manganese is because I can actually infer it from the fact that the charge of the entire molecule has to be 0, and I know that the oxygen's a -2. So if I look at my molecule, the oxygens are each -2, and there's 2 of them. Right? So I essentially have 4 negative charges. The whole molecule has to be 0, so the metal must be +4 to compensate. And so manganese is a +4 ion, and so to name it, I specify the +4 charge using a Roman numeral. And so I would call this compound manganese 4 oxide. Right. And it's that simple or that complicated, depending on how you feel about that. Again, iron is a transition metal. It has multiple oxidation states. If I make a compound with iron and chlorine, which is a halogen, again, since iron has, as we saw before, a +2 and a +3, I don't know just by looking at the iron what its charge is, but by looking at what it's bonded to, I can tell. Chlorine's a halogen. Halogens are always -1, so 3 -1s is a total negative charge of -3. The iron has to be +3 to compensate. And so my iron is a +3 ion. Right? And so I name it iron 3 chloride. We saw sodium fluoride earlier. Again, sodium here is a group 1. Fluorine is a halogen. Right? My halogens are almost always -1. My group 1s, my alkali metals, are always +1s. Right? In this case, there's really no choice. The sodium has to be +1 and the fluorine has to be -1. So I just call it sodium fluoride. Technically, I could call it sodium 1 fluoride because sodium is +1, but it's unnecessary to make that specification, and so generally speaking, you almost always see it as simply sodium fluoride. If there's only one oxidation state for the metal, meaning it's a group 1 or a group 2, first column or second column of the periodic table, I don't need to worry about the Roman numeral. Right? And not to belabor the point, right? CrO3, again, same deal as before. Right? Chromium is a transition metal, right? So it has multiple possible ions it could form. Oxygen is a group 6. It's always a -2, right? So there's 3 oxygen atoms, ions. Each of them has a -2 charge. That's a total of 6 negatives for the nonmetal. And there's 1 chromium. It has to bring the whole +6 to balance it. And so it's chromium 6 oxide. Right. And here's a couple more, right? NiO2, right? Again, nickel's in the middle. Oxygen is a -2. So here I've got 2 times -2, or a total of 4 negative charges. The nickel must be +4. And so I would name this nickel 4 oxide. And really that's it for ionic compounds. If I've got a metal and a nonmetal, right, the molecule formed is ionic, and the nomenclature I use is this ionic nomenclature. Metal first, nonmetal last, ending in IDE. For transition metals, I indicate the charge on the metal using a Roman numeral. Right? And of course, nomenclature works both ways. If I have the molecular formula, I can turn it into a name. If I have a name, I can turn it into a molecular formula. So nickel 4 fluoride has to be nickel with a +4 charge bonded to fluorine ions, fluoride ions, which are each -1. Again, it's a charge balance issue. If I've got 4 positives, I need 4 negatives. The smallest whole number ratio that does that is 1 nickel and 4 fluorines. And so if I read nickel 4 fluoride, I know that the molecular formula is nickel NiF4. Right? And so my naming is quite slick. It tells me exactly what the molecular formula is, and so it's easy to translate back and forth between the actual chemical composition and the name. Right. The one additional type of ionic compound that could be formed is from polyatomic ions, which sort of act as single units. Right? I can make a compound from a metal, which has a positive charge, and a nonmetal, which has a negative charge. I can also form an ionic compound from polyatomic, multiple atom ions. So nitrite is a nitrogen with 2 oxygens somehow stuck together. Nitrite has a -1 charge. Right? So I could, in fact, hook up a nitrite, a negatively charged ion, with a positively charged metal, in this case sodium. Right? The nomenclature is slightly different for the polyatomic ions, and in some sense it's a little simpler. Right? If I've got polyatomic ions, I simply name the polyatomic ion with no change in its name. This does require either knowing or having access to a table of the names. KMnO4, right, I have to recognize that MnO4 as a group is a polyatomic ion, right? Its name is permanganate, and it has a -1 charge. And so KMnO4 is potassium permanganate. Nitrate, right? NO3 minus, it's another one of my polyatomic ions, right? So it's always a -1. There's 3 of them. So again, it's -3 charges for the nitrate, and so the iron must be a +3, and so that's iron 3 nitrate. Notice I don't end in IDE. I just keep the ion's name as it was given to me. So generally speaking, I don't require my students to memorize these. I will always give you a table of polyatomic ions, but that's at your instructor's whim. Okay. And so all ionic compounds are either a metal with one or more nonmetals or some combination of polyatomic ions. All ionic compounds are named as we just talked about. Now metal ions, since they only form positive ions, generally speaking, will not form compounds. Mixtures of metals will form what are known as alloys, and those have very different properties, and are a little harder to name because they don't actually exist in fixed ratios. And so we won't talk about them